In the vast expanse of outer space, where extreme temperatures, cosmic radiation, and micrometeorites pose formidable challenges, the search for innovative materials is paramount. Enter foam metals, a groundbreaking class of materials that have emerged as frontrunners in revolutionizing space applications. Combining the structural integrity of metals with the remarkable lightweight and energy-absorbing properties of foams, foam metals offer unparalleled advantages in the hostile environment of space. Foam metals are a unique breed of materials that consist of a metal matrix with voids or pores distributed throughout their structure, similar to a sponge. This unique cellular structure grants them exceptional properties that make them highly desirable for space exploration. Their low density, compared to traditional metals, allows for significant weight reduction in spacecraft and satellites, enabling greater payload capacity and fuel efficiency. This advantage is of paramount importance in space missions where every gram of weight matters. Additionally, foam metals possess excellent energy absorption capabilities, which make them highly effective in mitigating the impact of collisions with micrometeoroids and space debris, safeguarding delicate equipment and critical components on board. Moreover, foam metals exhibit extraordinary thermal and electrical conductivity, enabling heat-efficient dissipation and electromagnetic shielding. These properties are vital for spacecraft, which must contend with extreme temperature fluctuations and the damaging effects of radiation in space. By incorporating foam metals into the design of spacecraft and satellites, engineers can enhance their resilience and extend their operational lifetimes while ensuring the protection and integrity of sensitive electronics. One of the most remarkable attributes of foam metals lies in their exceptional strength-to-weight ratio, which makes them a compelling choice for space applications. This ratio refers to a material's ability to withstand loads or stresses relative to its weight. In the case of foam metals, this property is truly remarkable, as they exhibit an incredibly high strength while maintaining a significantly low weight. The unique cellular structure of foam metals, with interconnected pores or voids distributed throughout the material, contributes to their impressive strength-to-weight ratio. These pores not only reduce the overall density of the metal, but also enhance its mechanical properties. By incorporating this porous structure, foam metals can achieve an optimal balance between strength and weight, surpassing conventional metals in terms of performance. In space applications, the high strength-to-weight ratio of foam metals offers invaluable benefits. Firstly, it allows for substantial weight reduction in spacecraft and satellites. Every kilogram saved in the design of space vehicles translates to increased payload capacity, enabling the inclusion of more scientific instruments, equipment, or supplies. Additionally, reducing the overall weight of the spacecraft can significantly enhance fuel efficiency, as less propellant is needed to overcome Earth's gravity and propel the vehicle into orbit or beyond. This leads to extended mission durations and greater operational flexibility, enabling longer journeys and the exploration of more distant destinations. Moreover, foam metals' high strength-to-weight ratio plays a crucial role in ensuring the structural integrity and survivability during space missions. Despite their lightweight nature, foam metals can withstand the extreme forces experienced during launch, orbital maneuvers, and atmospheric re-entry. Their strength enables them to withstand mechanical stresses, vibrations, and even impacts from micrometeoroids and space debris, protecting critical components and enhancing the overall reliability of the spacecraft. By enhancing the benefits of foam metals' high strength-to-weight ratio, engineers and scientists can push the boundaries of space exploration further than ever before. The reduced weight and improved structural integrity of spacecraft and satellites pave the way for more ambitious missions, from launching larger telescopes into orbit to facilitating human space travel and establishing sustainable space habitats. Foam metals are proving to be a vital ingredient in the quest to unravel the mysteries of the universe while maximizing the efficiency and effectiveness of space missions. In the harsh environment of outer space, thermal management becomes a paramount concern for spacecraft and satellites. With extreme temperature fluctuations, intense solar radiation, and limited avenues for heat dissipation, effectively controlling and dissipating heat is crucial for the optimal functioning and longevity of space systems. This is where foam metals step in as remarkable solutions, acting as heat sinks and other thermal control systems. Spacecraft and satellites generate heat from various sources, including onboard electronics, propulsion systems, and even the solar radiation they absorb. Without proper thermal management, excess heat can accumulate, leading to system malfunctions, degraded performance, and potentially catastrophic failures. Efficient heat dissipation is therefore of utmost importance in the demanding conditions of space. Foam metals offer unique advantages in thermal management due to their exceptional thermal conductivity. The interconnected pores or voids within foam metals facilitate the rapid transfer of heat, effectively acting as conduits for thermal energy. By integrating foam metals as heat sinks or thermal control systems within spacecraft, excess heat can be efficiently absorbed and conducted away from critical components. Foam metals not only dissipate heat, but also provide enhanced temperature regulation, Their high surface area to volume ratio allows for efficient heat exchange with the surrounding environment. This characteristic is particularly valuable in space, where radiative cooling is one of the primary means of heat dissipation. By leveraging the properties of foam metals, engineers can optimize the thermal balance of spacecraft, preventing overheating and ensuring stable operating conditions. Furthermore, foam metals can serve as effective thermal shielding materials. They possess excellent insulation properties, protecting sensitive electronics and instruments from extreme temperature fluctuations. This is vital in space missions where spacecraft can transition between sunlit and shadowed areas, experiencing significant temperature differentials. Foam metals act as thermal barriers, minimizing the transfer of heat and preserving the integrity and performance of onboard systems. Efficient heat dissipation provided by foam metals not only enhances the overall performance and reliability of spacecraft, but also extends their operational lifespan. Excessive heat buildup can accelerate component degradation and aging, shortening the mission duration. By effectively managing thermal loads with foam metals, space systems can operate optimally over extended periods, maximizing the return on investment and scientific output. Foam metals play a pivotal role in addressing the challenges of thermal management in space. Their high thermal conductivity, surface area to volume ratio, and insulation properties make them ideal materials for heat sinks, thermal control systems, and shielding applications. By harnessing the unique characteristics of foam metals, engineers can ensure efficient heat dissipation, temperature regulation, and system protection, enabling successful and prolonged space missions. The efficient thermal management provided by foam metals represents a significant step forward in advancing space exploration, enabling the realization of ambitious objectives, and expanding our understanding of the universe. Micrometeorites pose a persistent threat to spacecraft and satellites. These tiny particles, ranging in size from mere micrometers to millimeters, travel at incredibly high speeds, posing a risk of collision and potential damage. Understanding the potential hazards and implementing effective mitigation strategies is crucial for safeguarding space systems. Foam metals, with their exceptional energy absorption capabilities, have emerged as a promising solution to address this challenge and protect against micrometeorite impacts. Micrometeorites, originating from the various sources such as asteroid collisions or debris remnants from previous space missions, are characterized by their high velocities and kinetic energy. When they collide with spacecraft, they cause damage, ranging from superficial dents and surface erosion to more significant structural compromises. The energy released during these impacts can propagate through the spacecraft, potentially affecting critical components and compromising mission objectives. Foam metals possess unique energy absorption capabilities that make them highly effective in mitigating the damage caused by micrometeorite impacts. The cellular structure of foam metals allows for the dissipation and absorption of kinetic energy upon impact. As the micrometeorite collides with the foam metal surface, the interconnected pores and voids within the material deform and compress, absorbing and distributing the energy over a larger area. This deformation mechanism dissipates the energy and reduces the severity of the impact, protecting the underlying structure of the spacecraft. When it comes to shielding applications, foam metals indeed hold great potential. While they may not be the sole material used for shielding against micrometeorites, they can be incorporated into multi-layered shielding systems to enhance protection. The energy absorption capabilities of foam metals combined with their lightweight nature make them attractive candidates for spacecraft shielding. By strategically placing foam metal layers within a shielding system, engineers can enhance the overall energy absorption and distribution during impacts, minimizing the potential damage caused by micrometeorites. While foam metals offer numerous advantages and have proven to be highly promising for space applications, there are a few factors that may limit their widespread use in certain scenarios. It's important to consider these potential limitations when evaluating the feasibility of foam metals for future space applications. Here are a few reasons why foam metals might not be used extensively in some instances. Certain space applications may require materials with scientific properties that foam metals may not possess. For example, in situations where high stiffness or rigidity is crucial, traditional metals or composite materials might be preferred over foam metals due to their inherently higher structural strength. Each space mission has unique demands, and the selection of materials depends on a careful evaluation of the specific requirements. The production of foam metals can involve intricate fabrication processes and specialized equipment. Achieving consistent and controlled pore structures within the metal matrix can be challenging and may require sophisticated manufacturing techniques. These complexities can contribute to higher production costs and potentially limit the widespread adoption of foam metals. The cost of materials is an important factor in space missions, which often have budget constraints. While foam metals offer unique properties, their production costs and availability of suitable manufacturing technologies may currently be higher compared to more traditional metals. Cost effectiveness is an important consideration for space agencies and companies when selecting materials for their missions. It's essential to note that ongoing advancements in materials science and engineering may address some of these limitations in the future. As research and development progress, the potential applications and utilization of foam metals in space may expand, making them more feasible for a wider range of missions and spacecraft designs. In the realm of space exploration, foam metals have emerged as trailblazers, pushing the boundaries of materials science and revolutionizing space applications. With their unique combination of lightweight structure, energy absorption capabilities, and thermal properties, foam metals have become indispensable tools in addressing the challenges of space exploration. The remarkable strength-to-weight ratio of foam metals has allowed for significant weight reduction in spacecraft and satellites, leading to increased payload capacity and enhanced fuel efficiency. By incorporating foam metals into the design, engineers have unlocked new possibilities for ambitious space missions, enabling longer journeys and facilitating the exploration of more distant destinations. Thermal management, a critical aspect of space systems, has been vastly improved through the implementation of foam metals. Their exceptional thermal conductivity and insulation properties enable efficient heat dissipation, temperature regulation, and protection of vital components. The ability of foam metals to act as heat sinks and shielding materials makes them instrumental in safeguarding spacecraft from the extreme conditions of space. Moreover, foam metals have shown great promise in mitigating the potential damage caused by micrometeorites. Their energy absorption capabilities allow them to dissipate the kinetic energy of impacts, safeguarding critical structures and components. While there are limitations and challenges that currently restrict the widespread use of foam metals in certain space applications, ongoing research and development efforts offer promising avenues for future advancements. As our understanding of foam metals deepens and manufacturing techniques evolve, their utilization is poised to expand, further enhancing the safety, efficiency, and longevity of space missions. As always, thank you for taking the time to watch this video. If I missed anything or got anything wrong, please let me know, as I would love to learn more. If you liked what you heard, please consider subscribing. If you did not like what you heard, thank you for sticking with me this far. I appreciate the time that you've spent watching this video. No matter who you are, you only get 24 hours in a day. Thank you for spending a portion of that with me. See you next time.